Example, we're going to be working with a data set that we don't actually have all of the observations. The details of the data, we can't plug it into our calculator. So we're going to make sure we understand the setup of ANOVA, especially that ANOVA table. So this is an example coming from the Design of Analysis and Experiments, the author of that book. And he was hypothesizing about his golf game due to saying his best golf game was in summer and shoulder seasons because there was a less crowded course and he wouldn't get as frustrated and stay focused. So he believed his scores would be worse in the winter when the course is more crowded and he's more frustrated. So we have this data set here plotted out for us. We can see he has higher average scores in the winter compared to the other two. And our first question is, based on this plot, does it appear like there's more variability within the groups or between the groups? So remember, our within variability is this idea that, hey, I'm looking at the winter season and here are the golf scores. Even though I'm in the winter, there's still differences in your scores for each game. Even though I'm in the summer, there's still variability and differences. And the between variability is comparing that mean for each group, that average score during each season. So that highlighting is showing the between variability. And then this spread is showing the within variability. Of course, that spread cumulatively in all the different groups. Okay, so the question is, which one looks like it has more variability, within or between? So hopefully you're saying or thinking that there's more variability within. These scores are so spread out within each group that these slight differences, 89, 87, 86, might not really be meaningful. So I'll say something like that. There appears to be more variability within each group than, I don't know if anybody else does that where your head gets ahead of your hand there, more variability within each group than between the groups. And remember that between in this example is comparing the means of 89, 87, and 86. Looks like his scores vary a lot more than that within those than the averages themselves. And in the context of his research question, that means maybe the averages of the among the different seasons aren't really any different. Maybe we can't conclude that his research claim is true, that in fact he does better when the course is less crowded. So I'll say that as well. We may not be able to conclude that season influences golf game. All right, so let's check out the numbers and make sure our intuition is right here, that there's too much noise, too much randomness to say that these are really true differences going on between the seasons. So we don't have the data spelled out, but we do have kind of a partially filled in ANOVA table. So before we do that, let's just kind of see what we observe up here. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So it looks like my overall number of observations are 19. in this particular example. So as a reminder over here, n is 19. So let's fill this in. Our total degrees of freedom should be our total sample size minus 1. So our 19 minus 1, or 18. Our degrees of freedom for the treatment, or we called it factor in the last example, same thing, in the table anyway. So that should be how many groups we're comparing minus 1. So he has 3 seasons, minus 1 is 2. Error is just what makes this addition work. So 2 plus 16 is going to give me 18, or I can think of it with the formula, total number of observations minus number of groups will give me 16. Next column, we know they put the data in the calculator and gave us some information. This sum of squares is missing, but we can again use that idea of additivity. So 220.24 minus the 35.61 should give us 184.63 for our sum of squares error. So these two should add up to our total. Next, we've got the mean squares, and a reminder, mean squares is sum of squares over its degrees of freedom. So I get this mean squares by 35.16 divided by 2, and that should give you 17.805. This mean squares should be my 184 divided by 16, which should give us our 11.539. Our test statistic should be our mean squared factor over our mean squared error. So in this case, our 17.8 divided by 11.5, and that's going to give us our 1.543. And remember what this ratio is telling me. It's telling me that the variability explained by my factor is about 1.5 times that of the error. So it's not really that much more, actually. This ratio is close to 1. So these two values are fairly similar. It's about equal factor, equal error. So not a huge amount explained by the factor. When we find the p-value, and I apologize, there's a bit of a typo here. This should be 0.143. You should get this value. And now we can kind of wrap this up. We found all our values, state our hypotheses. So remember, we've got 3 means, so I'll do all 3 are the same. If you had 5 groups you were comparing, you would just keep extending this. All 5 are the same. So null, his average score is the same for all 3 seasons. HA is not all averages are equal. We're not able to give specific directions here. I keep spelling equal 2 L's. We're not able to give specific direction here. We're just saying that there's a difference somewhere. Our p-value and our test statistic. Here's our test statistic. Here's our p-value. And we can interpret that p-value and write our conclusion. So next bit, so there's step 2, step 3, step 4, let's do our interpretation. If the null is true, so if season has no impact on the average golf score, so if season does not impact golf scores on average, that's what our null hypothesis is saying, we would see data like ours. Or more extreme. .3% of the time, that's our p-value. All right, then based on that, if the null's true, season doesn't make a difference, then we're going to see our data 14.3% of the time. That's not super rare, so we can't rule out the null, and our conclusion is that we have little to no evidence for his research question, which we kind of saw coming from the picture. So there is little to no evidence that the average score is different in at least one season. And you could word this several different ways. You could say something like, there's little to no evidence that not all seasons have the same, or that there's a difference in scores or something. You can word that last part differently. As long as you're not saying every single one is different, you're just saying there's a difference somewhere.